These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos by going to my website. There's a link to the website in the info box. Here's the address of my website, www.freelance-teacher.com/videos.htm. That address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. I'll also mention that I offer tutoring via Skype, and you can find more information about that Skype tutoring service also at this website. And again, there's a link to that site in the info box. Thank you. I have prepared some handouts that cover the material that is covered in this series of videos. And in these videos, I'm going to be referring repeatedly to the material in those handouts. So it will be much easier to follow along with the videos if you have the handouts printed out in front of you while you're watching the videos. You can access the printable handout documents at my website. And once again, this is the address of my website. And it would be easiest to get there by just clicking the link in the info box.
Remember how we were talking about how bulkier things make more steric hindrance,
right?
So the reactivity goes down.
The SN2 reactivity,
right?
Because the big obstacle to SN2 is steric hindrance that blocks the nucleophile. Okay.
Okay. So I was reading that today, and so it was saying that it said that that's why the fastest is with like a methyl, and the slowest is with tertiary.
That's right, for SN2, right?
But then it said that elongation of the chain of a primary alkyl won't reduce the SN2 reactivity.
Right. Here it says that it does. It says like linking the chain by 1, 2 carbon reduces SN2 reactivity.
Right.
And here it says no.
Oops.
And then it says, do this trend continue as the chain gets longer? The answer is no. Higher alkyl.
Okay. And you're wondering why that is?
Yeah.
Okay.
It tried to explain it, but I didn't understand their drawing. Also, isn't it ethyl with 2 carbons?
Yeah, ethyl has 2 carbons. That's right.
Like here, it had 1.
Mm-hmm. So here's an ethyl and it has 2 carbons.
Mm-hmm.
The way it's supposed to.
Yeah, okay.
Okay, so here's a substrate that might do an SN2 reaction. Now, is this methyl primary, secondary, or tertiary?
Primary. No, it's nothing. It's not connected to a carbon.
Which means that it's methyl.
Yeah.
Methyl means 1 carbon. Yeah. Primary would mean that, so first of all, we should always identify the alpha carbon. Remember, the alpha carbon is the carbon that's attached to the leaving group. So here's the alpha carbon. And there it's cool with you if I recorded this? Yeah, okay. So, so it's always good to label the alpha carbon. Now this alpha carbon would be primary if it was attached to 1 other carbon. But it's not attached to any other carbons, so it's a methyl carbon. Okay, so is this very good for SN2 or very bad?
Very good.
Yeah, this is the best for SN2. All right, now I made this into an ethyl group. So what type of alpha carbon do we have now? Methyl, primary, secondary, or tertiary?
Secondary? I mean primary.
Primary.
Sorry.
So did we just get a little bit better for SN2 or a little bit worse?
Worse.
A little bit worse. Why? Because this carbon over here will sometimes get in the way of the nucleophile. Well, what's the nucleophile supposed to do?
Come in and attack.
The nucleophile is supposed to come in and attack this alpha carbon. Well, you can see that this isn't just the right place to get in the way. This carbon over here could get in the way and block that nucleophile. So now we see why a methyl is worse, why a primary is worse than a methyl. Okay.
Why is a cyclic something, why is that worse than a long chain?
Cyclic, where did it say that? Is that in the textbook?
It was, I can find it. It was in one of the practice questions that we did.
Right.
It was just trying to, it was ordering them in
Right.
what was best and what was worse. I can.
Okay, well, we can come back to that. That's a slightly different idea. Okay, so we've seen that primary is worse than methyl. All right, now, let's add another carbon. So now we've added one more carbon. Now, is this methyl primary or secondary? Still primary. Still primary. It's still only attached to one carbon chain. Now the question is this going to add more steric hindrance? Well, maybe a little, but remember that what matters is steric hindrance that blocks the nucleophile from attacking the alpha carbon. But this is so far away from the alpha carbon that it's probably usually not going to get in the way. You can see how this could get in the way because it's right next to the path, it's right next to the alpha carbon. This is sufficiently far away that it's much less likely to actually block the nucleophile. All right, so maybe this would slow us down a little, but not very much. And then if I added even more carbons out there, it would have almost no effect because they're so far away from the alpha carbon that they're not actually going to provide steric hindrance. So that's why we said, what's the big obstacle to SN2? The big obstacle is steric hindrance, but it's not good enough to say that. Steric hindrance that blocks the nucleophile. Steric hindrance that's way off in the boondocks doesn't matter. The only thing that matters is steric hindrance that can actually be close enough to the alpha carbon to block the nucleophile. So I think that's what they were saying in the textbook. The first one or two carbons that we add to the alpha carbon, they are close enough to get in the way and block the nucleophile. But once we add even more carbons, they're almost never going to be in the vicinity of the alpha carbon, so they don't make a big difference either way.
Okay.
Okay, that's actually not a terribly crucial point, to tell you the truth. The key thing, most important, is just to ask, is it methyl, primary, secondary, or tertiary? You can see I didn't even talk about that in the table that I gave you in the handout. So for most problems, you just want to ask methyl, primary, secondary, or
They did
tertiary.
have problems like that in the problem set though.
That's right. Unfortunately, well, I can't guarantee, but oftentimes some of the problems in the homework are a little bit more subtle than you would see on an exam. That's worth knowing. I just wouldn't make it your top priority. That's worth knowing, but it's not what's most important. Okay?
Okay. Are you going through stuff in the book? Well, I just had a question on it because I read it like before I came. Well, you can do the questions that you came up with. Did you do
For SN2, you prefer an aprotic
one question?
solvent?
Aprotic. That's right.
Aprotic, yeah. And then for the other one, you prefer a polar one, so.
Apolar protic.
Aprotic.
So they're both polar. SN2 prefers the polar aprotic, and SN1 prefers the polar protic. You're always going to use a polar solvent.
Okay. First of all, what is this configuration called when you draw it like that?
The Fisher projection?
Fisher projection. When you switch something from this side to this side, is that like you're switching it from dashed to wedged?
No, dashed and wedged is vertical, isn't it?
Because
Right.
what they did when
Mhm.
we had this problem and then the bromine had to attack it,
Right.
and all they did was switch it to this side, and I thought that you had to switch it to up here.
Yeah, that's a good question. So let's see, you've got there H.
You know why they do it on our side? Because it does backside attack, so it comes from back here and it replaces this one.
So what was over here? CH2?
CH3, and then on the bottom CH2, CH3, and then Cl.
And the
And
nucleophile
then
was?
the bromine.
Okay, so this guy comes in, and that kicks off like this. So we're looking here at a SN2 reaction, right? So this is going to be an SN2. All right, now we've already discussed how to draw the product of an SN2, so let's review that. Let's use the redraw and modify technique. So I'm going to start by just redrawing the starting material. So far I've just redrawn the starting material, and now I have to make modifications step by step to get the right product. Well, obviously the first modification to make is to erase the leaving group and replace it with the nucleophile. Right. So here's the nucleophile. Now so far, have I inverted the configuration or retained the configuration? Retained. But we know this is SN2. So we want to invert the configuration, and we've learned there's a mechanical trick for inverting the configuration. What's our mechanical trick for inverting the configuration?
Single swap.
Any single swap. Any single swap. And that works for any type of diagram. I don't think we've used that for Fisher projections, but it works for Fisher projections just like anything else. So what they did in your notes is they swapped the bromine and the methyl. But they could have made any swap. They could have swapped the bromine and the hydrogen, or they could have swapped the bromine and the ethyl, or if you wanted to, you could have swapped the hydrogen and the methyl. You can swap any two groups. Any single swap will give you the opposite configuration. So what they did is they put the bromine where the methyl used to be, and they put the methyl where the bromine used to be, and now we know that since we made a single swap, we have the opposite configuration to what we started with. But again, any swap would have worked. So it doesn't have to be from a wedge to a dash. All right, this isn't really like going from a wedge to a dash because both of these are pointing towards you. So instead of thinking of it in terms of wedges and dashes, we should just think any single swap will invert your configuration. And that's definitely the best way to get the right stereochemistry for SN2. So let's review one more time. How do you get the right stereochemistry for SN2? First, draw what the product would be with retention of configuration, and then make any convenient single swap. That's a simple and mechanical way to do it.
Okay.